Um, Thank you, Professor Wiley. It's a pleasure to spend time with you today. By way of some background, my name is Scott Samuelson. I'm a professor of mechanical, aerospace, and environmental engineering at UCI. As noted on the slide, I'm also the director of the National Fuel Cell Research Center, which was established in 1998 by the U.S. Department of Energy and the California Energy Commission. My life research has been in energy, beginning and continuing in the area of combustion, but now with the challenges associated with combustion, focusing on what will affect all of you and be an integral part of your life, whether it's driving your pacemaker in future years, or powering your automobile, or providing your electricity, is the fuel cell. Fuel cells will be an integral part of the renewable future, along with solar and wind. Solar and wind are intermittent, but still very valuable resources. We need a stable 24/7 source of electricity to complement solar and wind, and I will present some of those aspects to you. So you should think of this as a lecture on the future for sustainable energy for both transportation and the provision of electricity. I'm going to start with something you're familiar with, which is the automobile, just to have you understand how it is that you travel from point to point in a vehicle that takes in gasoline and air, and through a process which we call combustion, transforms that energy bound in the fuel to thermal energy. That's something we in engineering can do something with. And with the automobile, we propel the automobile, as you see here, with the provision of useful power for society. Along with that comes another product that we would rather not have delivered, and that's called the exhaust. With respect to propulsion, and many of you came here to Irvine with jet aircraft. Here is a jet aircraft with the presentation of the engine underneath the wing. In this case, we compress the air to a high pressure and high temperature before we add the fuel. We again have combustion, and then that provides us with that thermal energy. It's giving up that energy that's bound in the fuel to something we can do something with. And in this case, we provide a propulsion force to push that aircraft ahead. But then that other product, exhaust, comes along for the ride. Many of us depend upon electricity. I certainly found that I did this morning when I woke up with our grid being down. The alarms did not go off. The lights did not go on. My computer did not go on so I could refine this presentation this morning. In fact, that's the place where that presentation was up until 10:30 when the lights came back on. In that case, we're after electricity. And this particular engine, called the gas turbine, is something we use to produce much of our electricity today. And it's really the go-to technology where we take this off of the wing, place it and bolt it to the ground to provide not jet propulsion, but electric power. In that case, we take away this nozzle and we replace it with another turbine and electric generator to produce the electricity that we all depend upon as we do at this very moment. That's the useful power. And then along comes with that, what? The exhaust, right? So if we go to a kind of a mechanical engineering description of this process, we have a box that's being fed with fuel and air. We have the combustion that's giving rise to that thermal energy. And then depending on the engine we're using, we produce that useful power. That's what we're really after for all of us to be able to utilize. But there's that other deliverable right here, the exhaust. So I'm going to take a moment and tell you why I'm focusing on the exhaust. And that is because of the fact that combustion produces 80% of the world's power today. You think about that, from the aircraft to the automobile to the truck to the ship to the locomotive to the provision of electricity. It served us very well for more than 100 years, but it has this exhaust. And that exhaust is made up of what we call the major products of combustion: CO2, water, and nitrogen. That's almost 100% of the exhaust. And then in very small amounts, we have these other things that come along, and those are called pollutants. We'd like to ignore those. From an energy point of view, we do. They don't really amount to much. But Mother Nature has arranged for those pollutants to do something, to keep us aware that we need to be good stewards in the use of natural resources. One of those things that it does is to produce photochemical oxidant, which here in the Los Angeles area has been a challenge since the early 1940s. We call that smog. It's not the right term. It's really a photochemical oxidant, but nonetheless, it affects the public health. We now have going over here another issue, the CO2, because it's increasing in the troposphere, and that, of course, we know is a greenhouse gas giving rise to global climate change. And just to put this into perspective, and this is really the main picture I'd like to have you retain as we go through the lecture today, is to look at this picture of the Earth. It's pretty big, about 8,000 miles in diameter, and you see upon that Earth a small little bubble, sphere, purple, right here. That's all of the air associated with the Earth. That's the volume of air associated with the volume of the Earth. If we spread that around the Earth, which of course Mother Nature did, it's a very thin onion skin, only 10 miles deep at most. And it's a precious resource that for 100 years we've contaminated with pollutants and carbon dioxide, and we're being told that this is not healthy. We've been working on changes for 50 years, reducing the emissions from automobiles, reducing the emissions from power plants, but it's not enough. And now we have this added issue of global climate change. And this is giving rise to a major shift in the way that we're going to have to do business in the next 100 years. But before I get to that, we're talking here about exhaust contaminating the troposphere. That's pretty serious, right? Something we don't think about, have you, is this right here, that air. That air goes into the automobile, for example. Do you think about that? No, you're thinking about that gasoline and the dollars per gallon or the cost per gallon. But just think about one tank full of gasoline. Today in US dollars, that's about $50 to $60. It's about 20 gallons and it weighs about 180 pounds. It's about a body weight. So my question to you is that when we consume that tank full of gasoline, about 350 miles, how many pounds of air do you process? How many pounds of air do you process? How many pounds of air go through your engine? Air is pretty light, gasoline's pretty heavy. A good guess is 10 pounds per 180 pounds of fuel. The actual answer is 2,000 pounds, 1 ton of air. Much of that is nitrogen. You know that from your physics. Some of it is oxygen, about 400 pounds. And so 400 pounds of oxygen are consumed with every tank full of gasoline. Have we thought about what Mother Nature does with that? How does she replenish that into our atmosphere? How's she doing in that regard? I'll just leave it at that for you to ponder. But it is a resource, it's an air resource. We depend upon it. Our food depends upon it, oxygen. And we're consuming it and expecting something out there to kind of replenish it and bring it back. So in summary, I just have a box here which shows that 80% of the world's power is associated with our use of combustion. Approximately 90% of the world's pollutants come from combustion. 94% of the world's CO2 comes from combustion. And with every tank full of gasoline that we utilize, we are consuming 400 pounds of oxygen. Now with that, let's look at what we're up against. These are the forces that are causing change to your future. I would say my future as well, but you have more of a future than I do. I'm probably going to survive fine on gasoline. You're going to find a very different paradigm. So those of us like Professor Wiley and myself, when we were your age, the computer was just being part of the collegiate life, these big mainframes. And of course, now we have them here. You should think of the same as the fuel cell. You're really, many of you just hearing about it for the first time today. It'll be an integral part of your life in the future. So it's just a chance for you to see why that is. These are the forcing functions. Urban air quality, we aren't doing enough to bring that to the quality that our public deserves. Climate change, we know that we have a major challenge there, and our current way of doing business is not acceptable. We have now the recognition that petroleum is a finite resource. We're probably going to reach what's called the peak of the Hubert curve in 2016, where we are using more than we're discovering. And now from our 9/11 in New York, we have fuel independence and national security. Not only in the United States, but every country around the world would like to be in full control of its energy supply. Those are the driving forces. The paradigm shifts are in transportation, in electric power generation, in building design, in conservation, and in the design of communities of the future. It's an extraordinary, exciting future. Who would ever thought we'd be able to re-engineer basically society from transportation, electric power generation? We're able to start with a clean slate. There'll be a transition, there'll be many decades, but that's what we are able to be involved in right now. How are we going to do it better in the next 100 years than we did in the prior 100 years? I'm going to focus on two of these, transportation, electric power. If you have questions on the others, we can go into those. But transportation and electric power make up about 70% of our energy portfolio, and so they deserve our attention. Let's begin with this automobile. We talked about the major products of combustion, and we talked about the pollutants. Here you see them actually identified: oxides of nitrogen, carbon monoxide, and hydrocarbons. This is a vehicle that operates on gasoline, as we saw, takes 1 ton of air to be processed, and the overall efficiency of this vehicle is 16%. That means of the $50 that we spend to fill up the gas tank, we're basically throwing away 84% of that in heat. Or the 180 pounds of fuel in the tank that you're carrying around with you, 84% of that weight will just go into heat and have no useful purpose. So you can see right away that's sobering, 16%. Let's see if we can't do something better than that. And we're going to focus on carbon dioxide because it's an indicator not only of the emissions of greenhouse gas from the automobile, but also it's an indicator of the efficiency. The lower the CO2 per mile traveled, the higher the efficiency of the vehicle. And I want to use this chart to provide us some guidance in that regard. It's a chart that shows the emission of carbon monoxide, the greenhouse gas, from 0 to 1. So it's normalized to what's called the gasoline vehicle. Of course, we just saw that, where the normal vehicle is going to be 1. And you see right here something very interesting, which is the amount of CO2 that comes from the vehicle. That's here in the orange, versus the amount of CO2 that comes from the generation and transport and refining of the fuel to your pump. Only about 12% of the energy that goes into the automobile comes from getting that fuel to the automobile. It's very impressive, actually. I would have thought it would be more than that. So are we okay at that point? That's going to be our normalization. And our goal is to take this number from 1 down to 0. Because what we're after is an automobile that produces 0 CO2, completely eliminating the emission of carbon from the automobile. One way to do that is to improve the automobile. We have the evolution of the hybrid combustion vehicle. And what that's doing is bringing an electric drivetrain to the vehicle, a big battery here, an electric motor here. What's the advantage of that? Well, let's look up here. Looks like maybe it improves the efficiency. That's a dramatic improvement, a factor of 2 with the hybrid vehicle. Really encouraging technology. And what it does, of course, it reduces the CO2, the water, the nitrogen, and the pollutants as well, correspondingly to that improved efficiency. That's a step in the right direction, and we already see that shift being deployed around the world. What if we take that vehicle and place it on this plot and see how it looks? It does what you expect. It reduces the emission of CO2 by about a factor of 2, corresponding to the increase in efficiency by a factor of 2. Something else that we can do is go to a zero carbon fuel. For example, hydrogen. It's one of the attractive features of hydrogen, no carbon. What that does up here is not much here, but it takes out of the exhaust any carbon-containing species. CO2, CO, and hydrogen, hydrocarbons. How does it look on our plot? It looks really good. It's actually not this good. That's what it looks like. Son of a gun. Kicked ourselves in the shins. In other words, it takes a lot of energy in the absence of advanced technologies to generate that hydrogen. But you note there's no CO2 emission associated with the fuel here. I'm sorry, with the vehicle. This is all from the fuel production. Well, what can we do about that? We can introduce something that we will call the hybrid fuel cell vehicle. So this would be your first glance at the role of the fuel cell in your future. Right here is the reciprocating combustion engine. Right here is the fuel cell replacing it. That's all it takes. And what that does is to put a fuel cell under the hood and change this up a bit, quite a bit. That's one of the remarkable features and attributes of fuel cells is their very high fuel to electrical conversion efficiency. What does it do over here? Well, right here it reduces the amount of air to 500 pounds that we are processing and the amount of oxygen that we are taking out of the atmosphere to 100 pounds per tank full of hydrogen. And over here we still have water, we still have nitrogen, but virtually no pollutant. What that does on this chart is to give us this signature, and that's correct, which is going the right direction again. It's better than the gasoline hybrid, but not quite as much as you would expect, but it's going the right direction, and that's why you're seeing, among other reasons, a fuel cell so seriously considered for the future automobile. Well, let's take a moment and look at the fuel cell. Here it is. It takes hydrogen into a channel. This channel is called the anode channel. And on that anode, the hydrogen reacts to give off some electrons, and as a result, a proton. That kind of gold area is called a electrolyte, and it says to the proton, you're welcome to go through from left to right. Happy to have you. But you electrons, you have to find another path. For us in engineering, that's fortuitous because we would like to use electrons to drive a motor, to drive a load, to light a light bulb. And that's what happens. The electrons come back to the other side. This is called a cathode. They're still electrons, but they're kind of exhausted. They've given up this energy for that light bulb. But they're still energetic enough to react with this oxygen to ionize it. That ionized oxygen combines with this hydrogen to form water. And that's the product you hear about from fuel cells, along with the nitrogen that was in the air that comes out as a product. This particular fuel cell is called a proton exchange membrane fuel cell. So we refer to it as a PEM fuel cell. And it operates at a temperature about 90 degrees Celsius. So we'll put that right there. And one of the things I want you to learn about is that there are different types of fuel cells, and they differ in the electrolyte, in this case the proton exchange membrane, and in the temperature that they operate, 90 degrees Celsius. That's a pretty nice temperature for your automobile, not much different than you have today. And this particular kind of fuel cell you can turn on and off like you do with your automobile today. So it has the right features for the automobile, and as a result it's selected for the automobile as the fuel cell for your future. If you look at the way the fuel cell would look underneath your hood, it would be a stack. It would have hydrogen coming to it. It would have air coming to it. And it would give out direct current to drive that motor of your fuel cell vehicle. And it would have the exhaust, which you now know is made up of water and nitrogen. What this looks like in the actual automobile are these examples. General Motors, Toyota, and Honda. So this is an Equinox from GM, a Highlander from Toyota, and a vehicle called the Clarity from Honda. There are other type of vehicles that are already also deployed in testing. There's the bus, the fuel cell bus in both Europe and some in the United States, quite a few in Japan. And a commercial vehicle is the forklift. This is commercial today, so I put it right here, I put now. There are companies, whether it's Coca-Cola or Walmart, Whole Foods, that are changing out batteries in forklifts in their distribution centers to fuel cells. Batteries take 4 to 8 hours to recharge. A fuel cell takes 4 minutes to recharge. A fuel cell, when charged, will run for many, many hours. A battery will not. So this is an extraordinarily popular early market for fuel cells today, is in these specialty vehicles, these forklifts. For these vehicles here, the projection is 2015 for commercialization. Some companies are saying 2014. So we are preparing right now, because that's not too many years away, 2 to 3 years, for this vehicle to be available to those in certain areas of the world to initially have access to, primarily Japan, Europe, and the United States in that time frame, 2014, 2015. The automobile companies have been committed to this since the late 1980s. They've invested billions of dollars to ride this technology. It's an extraordinary vehicle. You go bonkers to drive it. It's quiet, it's responsive, great acceleration, and just a real kick to have under your foot. We have to work on improving this signature though, and we're now to where that's a bit lower in the last 5 years. One of the sources of hydrogen in many countries, including the United States, would be coal, and that's not very attractive. Look at that carbon signature. we're looking at renewables. We get to that term renewable. So here you have renewable from the electrolysis of water from solar or wind. That's very attractive. And we have renewable by gasifying biomass. Not quite as attractive, but still relatively very attractive. You saw that change right there. This is our goal for natural gas. This is our goal for coal. This is our goal for renewable electrolysis. And this is our goal for biomass. We're well on the way to reaching those goals. And you kind of see the future looks very encouraging with respect to hydrogen being available from a variety of domestically sourced resources with a low carbon signature. Our goal, though, is still zero if we can come up with the technology to do that. I want to take a transition here from transportation we've been talking about to electric power. Before I do that, are there questions you have about the automobile? Yes?
Could you talk a little bit about the downside? I mean, it seems so perfect, but are there unintended consequences of transitioning to a hydrogen fuel cell, and what are some of those?
So the question is, what is the downside? It seems almost too perfect. And the downside is that it is too perfect because it's difficult for anybody to accept something that is that good. But time is showing that more and more there's an appreciation for it. There are three areas of concern that I identify. It would not be a downside right now, but a concern. One would be to assure that we continue on this path of generating hydrogen with a low carbon imprint. We really have to force that, come up with technologies that are economically viable to do that. The second is the hydrogen infrastructure for refueling. We're actually in a panic right now because we do not have that effectively deployed to where a market can be created. We must do that in the next 2 years, and that's a separate story, but that's a downside of recreating a new infrastructure for fueling. Fortunately, it's only going to be about 15% of the gasoline stations we have today that have to be retrofitted with hydrogen to serve the entire public. So that's good news. And then the third concern would be safety. Like natural gas and like gasoline, hydrogen is flammable. It has a few characteristics that need to be addressed from a safety point of view. I'll just mention two. One is an odorant, like you have with natural gas. So if there's a leak, you can smell it. And secondly, if it is ignited, it doesn't give off a highly visible flame. In fact, it's almost transparent. So a additive that would not only provide the odorant, but also a bit of color. So if it does ignite, you would be able to see it and then just stay away from it, like in an automobile crash. Another question? Yes.
In the process of using electrolysis of water to extract the hydrogen, it has a very small carbon footprint. So where does that carbon footprint exactly? Is that calculated in the production of the equipment or using chemicals, or where does that carbon footprint come from?
So the question is on this plot where we showed renewable electrolysis still had a carbon footprint. It comes from the transport of the renewable hydrogen to the point of use. We're expecting most of the hydrogen to be produced in large wind farms, which in the Los Angeles area are about 40 to 50 miles, Beaumont being one, Tehachapi another. So the transport of it here by truck would have a carbon emission. We expect, though, not to be transporting it by truck, but by pipeline. And the pipeline would almost bring that to zero because the electricity we'd use for the pipeline would use renewable electricity. So that little bit of the signature is based upon the assumption of truck transport. Let's transition, we'll take one more, thank you.
Yeah. In the research that I've been around at the University of Florida, we talk a lot about fuel cells, and most particularly the catalyst that's used to split the hydrogen and oxygen. Is it, are you using platinum as your catalyst for that in the cars? And if so, how do you see that demand for platinum in building fuel cells affecting the countries where platinum is most prevalent for extraction?
The question has to do with the need of a noble metal in these fuel cells. In the proton exchange membrane fuel cell that we've just described for the automobile, it does require platinum on the anode to catalyze the reaction of the hydrogen. The automobile companies and other researchers in the last 8 years have dramatically reduced that loading to where it's less than the loading that you have already in the catalytic muffler. So it is going to increase the demand for platinum, but with the process and progress that's being made in reducing that and in alternatives, it's expected to be not nearly the issue that you are anticipating from your research. Still to be proven, so we have to keep that high on the list of areas to keep a watch on. On the next fuel cells I'm going to introduce you to, no catalyst is required because they operate already at a higher temperature. And let's move to that. I want to go to fuel cells that produce electric power. We bolt those to the ground, so we have call them a stationary application. And to do the operation of the fuel cell, we have to derive the hydrogen from a source. That source is typically natural gas, and we take that through a reformer in order to create that hydrogen. Direct current is something we don't normally use in an application like this room. We use alternating current. So over here we have an inverter or a power conditioner to derive that AC. But otherwise, you see the basic principles there of a stationary fuel cell system. Proton exchange membrane fuel cells are being considered for stationary applications. They have some niche applications right now, but I don't expect they're going to be too successful in the long term. But nonetheless, one of the niche applications is for residential use. So this is a garage in a Southern California home with a water heater, washing machine, and dryer, and just enough space here for a fuel cell, about a 5 kilowatt fuel cell. This is one product that's being presented to the community by a company in New York called Plug Power. It's a little bit larger than what I have here, but nonetheless a pretty reasonable size for the garage. A company that's been particularly successful in deploying these fuel cells is from Hillsboro, Oregon. It's called ClearEdge. It has a beige sort of enclosure, and it looks like this right here. If I really look out in the future, what you might think about for a home or a dormitory, some sort of housing unit somewhere in the world, would be a unit where there's sun available for having photovoltaic on the roof, renewable, and then a fuel cell in the garage or to the side of the house. During the day, the photovoltaic provides electricity to the home, as you would expect here, but we can also provide electricity to the fuel cell. Usually, many of us are not at home during the day and there's excess electricity. And the fuel cell can be run in reverse. It can take the water that was produced the night before and electrolyze it back to hydrogen and oxygen during the day. So that when night comes, we can go to the fuel cell and ask it to operate in the forward direction and provide electricity to the house. In addition, you should also think about the likelihood of being able to provide hydrogen to your hydrogen fuel cell vehicle as well. Now, this has no connection to the grid, no connection to natural gas pipelines or a propane tank. It's renewable, regenerative, and non-fossil fuel 24/7 production of electricity, and with some water going into the system, hydrogen for the vehicle as well. It's just a concept, but I want you to think about the kind of epitome of a renewable operation of a home by integrating a photovoltaic panel with a fuel cell. I moved that up so I could introduce you to a larger fuel cell called a phosphoric acid fuel cell. It operates at 200 degrees centigrade with virtually the same chemistry as the PEM. This is the longest running commercial fuel cell in the world, about 20 years. Why haven't we heard about it? Because it's too perfect. Sorry. But it's hard to market something that's so good and doesn't make any noise and doesn't turn anything at all. It just sits there and hums like a transformer. How excited have you been to see a transformer around campus? Those little green boxes, stop next time and just listen to it. It's a little bit, that's what a fuel cell sounds like. Totally a disaster to market. But commercial for 20 years. In California, that's the state of California. In the last 5 years, we've been particularly successful in deploying now over 30 megawatts of stationary fuel cells. Each of those red dots represent a location for an installation throughout California. You also see a very interesting portfolio of applications. And this turns out to be essential for marketing because you've got to develop the confidence of the market that these things really work. And it takes quite a time to get a variety of applications up and operating to where a new customer can say, where have you done it before? You can say, well, over there, let's go visit it. And that's now evolving in California to where we're about at what we call the tipping point where this market will start to take off. Examples include for this phosphoric acid fuel cell, a hospital in St. Helena, that's a 400 kilowatt fuel cell, and also a grocery store in San Diego, in Albertsons. This fuel cell produces electricity at 40%, 42% fuel electrical conversion efficiency. But remember, it runs hot. So the heat goes out of the exhaust and goes into a box at this Albertsons, and that box provides cold water that displaces a lot of the energy that goes into the refrigeration systems in grocery stores. Think about walking through a grocery store. You got all those open refrigeration units, right? Takes a lot of energy. In this application, the heat coming out of the exhaust, that would otherwise go to the atmosphere, is being captured. It's called cogeneration, turned into cold water and displacing electricity that would otherwise be used for that refrigeration. The heat coming out of that absorption chiller is even lower temperature. Rather than throwing it away, it goes through a desiccant. What's a desiccant? It's a material that is absorbing moisture from the market. When you're in the grocery store, there's actually a lot of moisture, and they have to dehumidify that. And often they take the air out of the building, put it through a desiccant that absorbs the water, and then brings back in the dry air. You need to regenerate that wet desiccant. So by taking the low quality heat out of this unit, you can regenerate that desiccant. The overall efficiency jumps up to 80%. That's a whole new paradigm called cogeneration. Just keep that in mind. Combined heat and power, combined cooling heat and power. It gets into building efficiency, but just want you to be aware of the utility of using power generators at the side of their application. The world's record right now for energy efficiency is 92%. It's a casino in New Jersey that has exactly this system, and in the winter it takes the low temperature heat out of the desiccant, which is just basically a throwaway, maybe 125 degrees Fahrenheit, and puts it through the sidewalks to keep them from icing for safety of the customers coming in the casino. Overall efficiency of 92%. It's really, really a nice feel of future. This unit produces no pollutants. Remember, virtually no pollutants. An up-and-coming new fuel cell technology is called molten carbonate. Many of you will be working with this in your professional work. This has a very different chemistry, as you can see, but notice the very high temperature it operates at. So we call that a high-temperature fuel cell. Very successful in California. Most of the 33 megawatts today are of this type. This is at a university, Cal State Northridge University. This is a 1 megawatt installation. You can see rather than a concrete block fence around this unit, you can see. Because right to the left of this picture is a student center. And students come out and look at this, and it's to cause them to become curious. So the kiosk right here where they can come over and learn about this future and the fact that their university is one of the first in the nation to deploy this technology. That's molten carbonate. Another application that you'll be much more aligned with is the Sierra Nevada Brewery in Chico, California. If you're on to only have Sierra Nevada beer, knowing that it's being produced by a fuel cell. The fuel cell is driven not by natural gas, but by a digester that's processing the beer waste and producing a digester gas. And here you see 1 megawatt of power, and then the heat goes into the digester to support it, again with an overall efficiency of 80%. This is truly a renewable application, so I'll put up the word renewable. This is a wastewater treatment plant in the middle of California called Tulare, small town, that has 1 megawatt operating off of the biogas produced from human waste, and then the heat goes back into supporting the digesters that is processing that human waste. This is a very rapidly developing market in California, with now 12 megawatts deployed. It says 9 there, but in the last 4 weeks, 3 megawatts have been added out in Chino, California. And a hotel, 1.5 megawatts of a Sheraton. The holy grail of solid oxide fuel cell technology is called solid oxide fuel cell technology. You can see that it operates at an even higher temperature. It became commercial really about a year ago, January, by a California company called Bloom Energy. They make the units in 100 kilowatt modules. This is at eBay in Silicon Valley, so that's 500 kilowatts. This is at Google, 400 kilowatts. This is at Caltech, 2 megawatts, very large installation there, again a university, and then a Walmart facility in Hemet of about 600 kilowatts. So that kind of gives you a feel of the early market, what they look like, how they perform, and why they are going to be so very popular. From a political point of view and a business point of view, I wanted to share with you an experiment by the University of California, which was to establish a collaborative in 2001 that has as a board of directors a unique group. They're called government agencies. They involve California agencies that are somehow involved in fuel cell technology. It might be in the technology development, such as the California Energy Commission, in the regulation of fuel cells, such as the California Air Resources Board or the California Public Utilities Commission, or in the actually acquisition of fuel cells for buildings in California, such as the California Department of General Services. We added to that the federal agencies, Energy, Defense, GSA, and EPA, and then regional agencies. And this group meets twice a year in Sacramento to talk about how the agencies can collaborate, cooperate, and share resources, what kind of policies are needed and need to be advocated for. And it's been an extremely powerful and successful activity to spawning the market of 33 megawatts that you see here. Now, policy is very important. Over the last 10 years, we've gone to 33 megawatts in California. In Korea, in the last 5 years, they're approaching 200 megawatts. They've gone from 0 to 200 megawatts in 5 years. That's 5 times more than we've been able to garner in California in 10 years. What's the difference? It's a policy. The policy is called a feed-in tariff. Just now being introduced in California, but when you think of markets, you have to think about, of course, policy, particularly markets that are so different than what we are used to. The companies that are driving the Korean market are U.S. companies, UTC Power with phosphoric acid, and Fuel Cell Energy with molten carbonate. So ironically, today, the United States has a leadership in fuel cell technology, but we're exporting almost 5 times more than we're deploying domestically. Policy. And to address policy, there's this industry advisory panel headed by one of the members, and here's the makeup of the industry advisory panel, that meet the day before to identify the kind of market constraints that are being faced and to convey that to the board of directors to consider the following day. So a bit in summary, this is where fuel cells are being deployed today in major markets, industrial applications, hospitals, office buildings, hotels, and in wastewater treatment plants for that renewable 24/7 application. I also indicated that ClearEdge is beginning to deploy fuel cells in residential applications. We see in the future, maybe not too distant future, utilities acquiring fuel cells to support the grid at pinch points. And we call these Tiger stations, or Transmission Integrated Grid Energy Resource. With respect to central power plants, you can see the manner by which we typically in countries produce central power. Combustion providing the most of it, as we have seen. But the type of technology that's evolving for central power plants is an integration of fuel cells with gas turbines. It's called hybrid systems. We don't expect those to be deployed for another 15 years, but the design is well underway. For power plants, it would have 75% efficiency on natural gas, for example, zero emission of criteria pollutants, and sequestration-ready CO2 effluent. What drives markets? Significant grid constraints would cause you to go to a fuel cell. I wish I had one in my home this morning. My wife asked me why we didn't. I didn't really have a good answer for that. I would have no problem. I would have had this presentation in much better shape. But faced with high electrical prices, because that's grid electricity, if you can produce it in your own fuel cell at less, that's going to benefit you. Also, low natural gas pricing. In the United States, with this discovery of fracking, that's dramatically increasing the rate of this new market with stationary fuel cells. And then where you have air pollution problems. So here where you see hatches and reds, those are where the early markets have been evolving for fuel cells and in any country. But in Korea, they have a policy that's encouraging any one of us to purchase a 60 megawatt fuel cell power plant and feed it onto the grid because we can make a lot of money. We just need to come up with the $100 million of capital at the beginning to get started. Attributes of stationary fuel cells: a high fuel electrical efficiency, a high quality heat, acoustically benign, virtually zero emission of criteria pollutants, and a fortuitous fit for this distributed generation where you apply it at the point of use because it doesn't make any sound, it doesn't emit any pollution. You have people around like you do in this building, and that's why fuel cells are working so well. A partner, I think I just want to share with you the other attributes of distributed generation. I'll just move on. The partner for renewable solar and wind that I alluded to right at the beginning. It also provides a 24/7 baseload power and heat. It's very effective in meeting AB 32. Now AB 32 you may not have heard about. Professor Demento mentioned that this morning. But that's the Kyoto Accord for California. So California, by law, must reduce its emissions by 2020 to the 1990 levels. So this is the track we're on. We must get these down by law to 1990 levels by 2020. That's a 30% reduction. And not quite by law yet, but by governor's directive, we must reduce this by another 80% by 2050. That's really the Kyoto Accords. In California, because the U.S. hasn't adopted them, has gone ahead to adopt them. So we are on a very major track to reaching this goal, and all these attributes give rise to a very major resource of fuel cells to achieving that. and now we're starting to see market demand. Questions that are regularly asked about stationary fuel cells are, is it a proven technology? So I mentioned the 20 years already of commercialization, a wide portfolio of applications, a burgeoning track record of deployment, and a critical role of the DOE investment in early years, 1970s in particular. Are there megawatt class technologies? The answer is yes. We just had announced last week a 60 megawatt deployment to Korea, so we're in tens of megawatts now. Renewable operation, over 10 megawatts deployed in California alone. Environmental footprint, remarkably benign. Financing, there's strong incentives to buy down the high cost of fuel cells today. And I say here, the cost is competitive today, but we're on a path of acceleration to reducing that cost. This basically shows the cost in dollars per kilowatt installed by fuel cells, 2003, 2005, 2007, 2009, 2011. So you can see that the price is coming down with deployment and mass production. Other surveys that have been taken show similar trends. Our goal is about $1,000 per kilowatt. That would be competitive with gas turbine engines. But due to the actual attributes of fuel cells, we're seeing fuel cells to be very competitive and successful at $2,000 per kilowatt. And you can see that we're rapidly approaching that goal. So that's stationary. Let me bring in transportation and just describe to you a very interesting technology to give you some encouragement of what the future portends. Remember, this is the stationary fuel cell with the fuel processor and the power conditioner. Let me bring back the mobile fuel cell. Where is it? There it is. And what this is bringing to your attention is that the stationary fuel cell is producing hydrogen to produce electricity, and the mobile fuel cell down here is desirous of hydrogen as a fuel. And it kind of creates this thought of using the stationary fuel cell to produce hydrogen. Let's see how we might do that. Here's a hydrogen station. It happens to be the most popular in the world today, the most in demand, the most advanced. I'm about ready to say I can't say that anymore, and I probably can't say that anymore, because we now have an increasing population of new stations coming online. But up until last month, this was the most advanced, most popular in the world. It's located here in UC Irvine, and the reason it's so popular is that all the automobile companies in the world have been using this area of the world for testing these vehicles for the last 10 years. And this has been the station that's been supporting Toyota, Nissan, Honda, Hyundai, Mercedes, General Motors. All the vehicles are operating here out of the station. The station is supplied with liquid hydrogen from a processing plant in California that produces it from natural gas. But what if, instead, we brought in a stationary fuel cell operating in natural gas, provide electricity over here to a customer, these condominiums, provided heat and cooling to those condominiums, and then on demand provided hydrogen to support the station. It seems like a simple concept. What I want you to understand is that today that's the most energy efficient and environmentally responsible way of producing hydrogen 24/7. We call that an energy station. Now, if instead let's use natural gas here, and here it is in a cartoon version of how it would work. Let me just show you why it's so successful. There's a synergism, and this is the first example that I want to share with you too, where let's put into this fuel cell some natural gas, 100 megajoules of natural gas, and out of it we'll get 47 megajoules of electricity and about 53 megajoules of high-quality heat. That's the way the fuel cell, at least molten carbonate, operates. If instead we change to a tri-generation mode, where instead of 1, 2, we add the generation of hydrogen, we can do that by increasing the input of natural gas by 43% and putting in 143 megajoules of natural gas. Over here, we still get 47 megajoules of electricity, and we can still get 53 megajoules of high-quality heat, but we get now 43 megajoules of hydrogen. And the reason the efficiency is just about 100% is due to the synergism. The higher the hydrogen in the anode, the higher the efficiency of the fuel cell. Most of you who have had chemistry know that when you increase the concentration of reactants, the faster the reaction. Same principle is here. Typically we don't do that because we don't have a use of the hydrogen. But now we've come up with the use of the hydrogen, and that is to support a hydrogen fueling station. Now what if instead of natural gas we bring in another supply of fuel, renewable fuel? So this is to Professor Whiteley's renewable energy concept. I told you I'd bring in little snippets of it. What we get out of this now would be a renewable energy station with the electricity, the thermal product, and the hydrogen all coming from a renewable resource. Pie in the sky? Possibly. It does reach this goal of zero carbon because we're using human waste to produce the fuel. Show you how this would work. This is a schematic of a wastewater treatment plant. All of you should be aware of this. All of you should visit one day to know what is being done with our human waste. We'll call that sludge. It goes into a digester that has to be heated. One of the products is a gas called anaerobic digester gas that's rich in methane. Today it can be sent to the boiler to operate the boiler to produce that hot water. With a stationary fuel cell, it'll come from up above, which we often call heaven. That's almost as good as perfect, right? And it produces now the hot water, but it also, at the same time, produces another product, electricity. In this example, it could be hundreds of kilowatts or megawatts. And this is what's deployed around 10 megawatts in California. That's why it's so successful. This new technology where we kind of bore into the fuel cell and extract out hydrogen on demand is the unique feature of this, biohydrogen. And this picture is really the epitome of sustainability. It's using human waste to produce electricity, which we need, heat or cooling, which we need, and then the transportation fuel, which we desire, all from human waste. This is actually in operation today about 10 miles from here, north, at a facility called the Orange County Sanitation District. It was commissioned about 1 year ago, and today you can actually go and obtain hydrogen from the human waste at that particular station. This was a strategic alliance of these companies. You'll find this technology probably being deployed in many different areas as time goes on to produce hydrogen from various domestic sources around the countries. Synergism 2, and we're getting close to closure, is coming back to our gas turbine that's generating electricity. If we take the combustion away and replace it with a fuel cell, it turns out that the fuel cell operates much better. It likes a pressurized environment, something 15 years ago we didn't know. And it gives rise to the oxidation of fuel and air to drive the turbines, but at the same time producing electricity that the combustion alone did not do. Notice no electricity here, producing pollutants. Here, electricity higher conversion of fuel to electricity and no pollutants. So we're projecting fuel electrical conversion efficiencies of 60%, 70%, and even above 70% in the future. This is called a hybrid fuel cell gas turbine. And where is it going to be deployed? Well, let's look first at how it looks on this map. This is a plot of efficiency of the power generator as a function of its size. So 1 kilowatt is like a home. 1 megawatt is a hotel. 10 megawatts would be a university. Here at UCI, our peak load is around 28 megawatts. And then in central power is 1,000 megawatts. We populate this space with gas turbines today, and you can see we're getting up to higher and higher efficiencies. To do that, we have to go to larger units. And there's a thermodynamic boundary based upon the Carnot efficiency of about 65%. And we're getting pretty close to that with current systems today, very impressive with high distributed generation applications or central power. Kawasaki particularly is deploying one of those HAT human air turbine cycles today. Where does a hybrid pencil out? Right here today. It's operating in Montana at 53%. Tomorrow, 65%. And then in about 10 years, we believe, approaching 80%. And not only is the efficiency going up, but the range of application is going up as well. Very attractive for distributed generation. This is a picture of the kludge. It was first tested here in 2003, the first commercial deployment in 2007, and a commercial version that Rolls-Royce plans to deploy in the next 2 years. We're going to see them in distributed generation, in industrial plants, hotels. We're going to see them at tidal stations, and out here at, as I mentioned earlier, central generation. It's a fascinating integration of a heat engine with a fuel cell. Other places that you'll see it would be locomotives, a very major project going on with Union Pacific, General Electric, and repowering locomotives for the future. Today, diesel electric, 30% efficiency, substantial emission of pollutants. Can you imagine this being at 75, 80% efficiency, zero emission of pollutants, and acoustically benign? Propelling ships, long distance trucks. Really? This application would not be for propulsion. Airbus and Boeing are right now competing vigorously for the first to have fuel cells on board. In the Paris Air Show last year, Airbus had an airplane that said right along the top here, fuel cell powered. Not for propulsion, but for hoteling, providing the hoteling on the aircraft. Boeing and Airbus are competing for the most environmentally sensitive and sustainable aircraft in the world, and hoteling as a big part of having a competitive edge, and fuel cell hybrid systems are the technology of choice. So somewhat ironically, while this seems a little bit out of it, this will be the first commercial application other than distributed generation. So these are the 2 areas that we focused on: transportation, electric power. We went through these examples. And we also have electric vehicles as well. So why don't we take questions at this moment and perhaps conclude as well. Let's go to questions that you might have.
Let's thank him first.